Hello everyone, my name is Raymond Ho. I am a research engineer from Quantum Communications Laboratory at National University of Singapore, and today I would like to present our poster in Qcrypt 2022 conference, which is titled Analysis and Characterization Methodology of High-Speed Balanced Homodyne Detector using RF MMIC Amplifier for Quantum Communication. This is a joint work with RF MMIC Modeling and Packaging Laboratory at National University of Singapore as well. Balanced homodyne detector realizes a pHEMT of the quadrature of an electric field with noise term which corresponds to the efficiency of the process. How people typically do it is by mixing a strong coherent source, which we will call local oscillator, with the signal at a 50-50 beam splitter. The output of the beam splitter will be detected or converted to photocurrents using two photodiodes, and then we subtract one photocurrent from the other and amplify the subtracted photocurrent using a component which is called a transimpedance amplifier, or TIA for short. This component converts a weak current signal into a voltage. So in the end, at the output of the TIA, we have a time series of a voltage which needs to be processed for us to be able to infer some statistics of the quadrature that we want. In general, there are two types or two configurations of TIA. The first one on the left is called shunt feedback TIA, and the second one on the right is just a resistor and a voltage amplifier, which can be separated by a transmission line. The configuration on the left, which is the shunt feedback TIA, is more common for balanced homodyne detector, and not only for BHD but also for optical receivers in general. And the reason is that this configuration has lower noise if we fix the gain and the bandwidth. So this can be shown from a lumped circuit model or lumped component model of the electrical circuit. In this work, we show that one can still get a short noise limited performance using the configuration on the right. Although having lower liberty to control the electrical noise, there are some reasons in which mainly it's a practical limitation in which people might not be able to do or to realize a circuit on the left. So in that situation, people as an alternative can also use the configuration on the right to do a balanced homodyne detector as well. So we propose some methods to characterize the balanced homodyne detector using the configuration on the right just now. The first thing to characterize that we think is important is the response of the amplifier, which can be represented by the two-port scattering parameters, S2 parameters for short, which can be measured using factor network analyzer. From these S2 parameters, one can deduce the gain response, the group delay, reflection coefficients, and all other parameters, which shows how the amplifier changes the time series, the voltage time series of the output, which is really important if you want to know what is the effect of the amplifier on the measured quadrature or some statistics of the quadrature. So the figure on the left is the power gain of the amplifier, which represents the gain response of the amplifier, and on the right we have the group delay of the amplifier, which shows how much delay the input signal has at a certain frequency. Other than that, we can also characterize the noise figure of the amplifier, and together with the S parameter, the response of the photodiode, and the output reflection coefficient of the photodiode, one can deduce, or one can predict the noise spectrum, either the electrical or the quantum shock noise spectrum that we will get in the experiment. So essentially, using all these parameters, if one can characterize them accurately, then using a theoretical model, one can calculate what is the expected noise spectrum and then compare it to the experiment. So from this prediction, one can also see how much shot noise clearance that one can get before performing the experiment. And then one can do a comparison with the value that that one get from the experiment. So this is one of the typical figure that we'll get from this characterization, where the dashed line is the model prediction and the solid lines are the experimental data. One can also check the linearity, which is important because we need to ensure that the photodiode needs to be in a linear working regime. And one of the way to enforce them to be in the linear working regime or approximately linear working regime is by ensuring that both the photodiode and the amplifier is below the 1 dB compression point of the respective devices. So 1 dB compression point is the point at which the gain of the amplifier or the response or the responsivity of the photodiode drops by 1 dB. So by ensuring that we are well below this 1 dB compression point, we can be sure that we are working in a linear regime. And this is confirmed by measuring the fluctuation or the quadrature of pHEMT as a signal and plotting the integrated power of this noise spectrum or the pHEMT noise spectrum with respect to the LO power. And one can see from this graph that it is approximately linear as expected. That's our work, and have a great day at the conference.